To understand the logistics of the Indian Railways, you have to start with the sheer numbers. With over 1.4 million employees, it is the 8th largest employer on Earth, responsible for moving millions of passengers every single day. But this modern torrent of humanity flows through a legacy infrastructure built largely from Victorian stone and steel. When a system this heavy relies purely on human operators pulling analog levers, the strain eventually reaches a breaking point. Ticketing portals buckle under the traffic, and trains stack up on the tracks waiting for manual clearance. Under that kind of constant pressure, human fatigue introduces deadly variables. A tired driver missing a red light, known as signal passing at danger, or SPAD, becomes a highly dangerous statistical probability. Adding more human workers to the system can't solve a mathematical limit. To keep operating, the railway is implementing a 3-tiered digital pipeline: data analytics to read the network, machine learning to make decisions, and robotics to physically execute them. The physics of moving millions of tons across thousands of miles require that this heavy infrastructure move toward a state of constant synchronized automation. Think of data analytics as the railway's sensory organs. Its entire purpose is to take an overwhelming, chaotic flood of raw passenger and operational information and filter it into clear, usable trends. To make data usable, it runs through a strict 5-step cycle: establishing the specific requirement, collection from massive internal logs, cleaning out the unusable junk, deep analysis of the patterns, and finally communication through visual charts that engineers can actually read. We can see the cost of poor data handling in the legacy IRCTC ticketing portal. For years, the servers would frequently freeze and crash almost instantly during peak booking hours because the massive incoming data requests were entirely unoptimized. By running those millions of daily user interactions through the analytics pipeline, engineers isolated the exact bottlenecks slowing down the servers and optimized the data flow. The resulting speed increase allowed the system to process an additional 1.3 million ticket bookings every single day, completely stabilizing the platform for passengers. Clean, actionable information is the absolute baseline required to stretch a 19th century railway to meet high-speed consumer demand. Once you have clean data, you need a way to interpret it. Artificial intelligence, using the framework first defined by computer scientist John McCarthy, gives machines the intellectual capacity to weigh variables and make logical decisions. Machine learning is the operational engine inside that AI. Instead of waiting for a human to write new code for every possible scenario, the program dynamically learns from incoming data and rewrites its own rules. This processing happens in 3 main ways: supervised learning, where the AI is given clear targets to hit; unsupervised learning, where it digs through hidden data to find new patterns; and reinforcement learning, a highly complex trial and error process used to adapt to dynamic environments. The Indian Railways feeds its cleaned analytics data straight into these specific algorithms. The models crunch historical travel times, track layouts, and weather to build highly efficient, self-correcting train schedules. These predictive algorithms also actively monitor track hardware and adjust train speeds in real time, effectively intervening to prevent those deadly signal passing errors before they happen. By spotting failures before human operators can, machine learning turns passive historical records into active, life-saving foresight. But an algorithm can't turn a wrench. Robotics provide the physical muscle, combining mechanical and electronic engineering to let AI interact with the real world. We see this directly in passenger areas, like the Pune station deploying a robot named Captain Arjun to handle automated thermal screening and passenger security monitoring. For heavy infrastructure, the Nagpur division uses a specialized rover known as UUSTAD. It rolls directly underneath the train carriages to physically inspect the undergears. Armed with HD cameras and LED floodlights, UUSTAD streams high-resolution diagnostic video over Wi-Fi, allowing engineers to inspect dangerous, hard-to-reach areas safely from a remote screen. These machines form the vital bridge between invisible algorithmic intelligence and the heavy, perilous work of keeping thousands of steel trains rolling. The operational math is clear. Robots operate continuously, 24/7, with zero human fatigue, significantly outperforming manual labor in dark or hazardous environments. However, introducing relentless automation into a massive workforce creates immediate friction. Every diagnostic task handed to a rover presents a legitimate threat of mass job displacement for workers who rely on physical labor wages to survive. Beyond the human toll, there is a severe capital requirement. Deploying advanced sensors and maintaining these AI ecosystems requires continuous power supplies and extremely expensive specialized repair technicians. So the railway extracts millions of data points every day, runs them through algorithmic processing to find the safest routes, and increasingly relies on robotics to carry out the physical execution. This digital pipeline has transitioned the railway into a data-driven utility, where physical hardware is controlled by an integrated software layer. To handle the staggering physical demands of modern transit, heavy industry has no choice but to surrender physical control to invisible digital intelligence.